Welcome to the deep dive. Today we're tackling something pretty ambitious. We're weaving together three threads that honestly seem worlds apart at first glance.
That's right. We're looking at deep time archaeology specifically when our ancient ancestors got really clever with tools.
Then jumping way forward to the very foundations of civilization, how the first states got started in Sumer.
And then bringing it right up to the present, looking at the really concerning accelerating changes happening in our oceans right now.
Exactly. And our mission here is to try and uncover the connections, how seemingly subtle environmental shifts, things like coastal changes, temperature tolerances, resource availability, have actually shaped, well, everything. Life, human history.
It's all about environmental causality, isn't it?
Yeah.
Whether it's 400,000 years ago or looking ahead 40 years, these environmental pressures, they force change, they force innovation, restructuring.
Yeah.
Survival, basically.
It's a crucial perspective, that deep environmental context. So we'll trace how necessity drove technology, how geology shaped governance, and maybe most urgently, what losing key natural assets fast means for us today.
Okay, so where do we start? Back in the beginning.
Let's do it. 400,000 years ago, our early ancestors, and a toolkit that's maybe more sophisticated than we often think.
Yeah, this period, it's really seen as a kind of cognitive leap. You see hominins starting to relate to their environment differently. Researchers talk about a novel symbolic relationship.
Meaning, not just seeing food and danger.
Exactly. It's about seeing potential in raw materials. They started looking beyond the obvious, even using stuff that might have previously been considered, well, waste.
And that includes materials we don't always think of preserving well, like bone and wood.
Precisely. Take sites like Casal Lombroso near Rome in Italy. The archaeology there is fascinating. Hominins weren't just scavenging elephants. Proboscideans is the technical term.
Right, the big ones.
They were actively butchering them. But here's the really key finding. They were then taking the bones and making tools. Sophisticated ones.
Okay, but how certain are we? Could they just have been, banging bones around?
The evidence is quite specific, actually. They found what are called green bone fractures.
Green bone?
Meaning the bone was broken when it was fresh, still pliable, not old, brittle bone. And they found clear impact marks alongside these fractures. Crucially, the fractured bones themselves show use wear, like scrape marks, polish, consistent with being used repeatedly as tools.
Okay, so they were deliberately shaping them.
Yes, and not just crude bashers. The sources point out they were taking these large, thick proboscidean bones and shaping them into massive bifacial handaxes.
Handaxes, like the stone ones.
Exactly like the stone Acheulean handaxes.
Yeah.
That's what's so remarkable. The Acheulean design, it's this standardized, quite complex shape that humans used for hundreds of thousands of years with stone.
Right, a well-known technology.
And the fact that these hominins at Casal Lombroso and also at Reverdum Quarry in the Levant could replicate that same precise design using bone. Well, it shows a deep understanding. They grasped the design principle separate from the material itself.
They saw the potential in the bone. They weren't just limited to thinking stone makes tools.
Precisely. Seeing raw material where others might just see, leftovers from lunch, it's a cognitive jump.
That understanding of material properties like fresh bone versus dry bone, that must have applied to wood too, right? Even though wood usually rots away.
It absolutely did. And for that, the finds from Schöningen in Germany are just world-class. Really incredible preservation.
Yeah, Schöningen. That's the site with the skiers, isn't it?
That's the one. It gives us this amazing snapshot. 9 almost complete wooden spears, a lance, another worked stick, all found with the remains of, get this, at least 35 butchered horses.
35 horses, so serious hunting. But were the spears just like sharpened sticks or something more?
Oh, much more. Proper technology. Analysis shows they carefully selected the wood, usually thin spruce or pine trunks. They scraped them down, shaped the points, and even fire-hardened the tips.
Fire-hardened, okay, that's clever.
But the really stunning part is the physics. These things were balanced. The weight distribution, the dimensions, they're remarkably similar to the modern championship javelins.
You're kidding, like designed for throwing accurately.
Exactly. These weren't just for poking. They were designed to be thrown effectively, probably from a distance, to bring down large, fast animals. That takes planning, understanding materials, understanding aerodynamics. I mean, it's sophisticated stuff.
Tactical genius, really. Driven by the need to hunt big game.
Necessity again.
Okay, so 400,000 years ago, necessity drives this impressive technological adaptation. Now, let's take that promised massive leap. We're jumping forward hundreds of thousands of years and shifting focus.
From technology driven by necessity to social structures driven by necessity.
You got it. We're heading to Mesopotamia, Sumer, the cradle of civilization, but we're looking at what forced the emergence of those first states.
Right. This is where geology and, well, governance really smash together.
Yeah.
We often focus on farming, but you look at the early Ubaid culture, maybe 8,000, 6,000 years ago.
This is before the big cities?
Yeah, way before. You had these small, scattered villages across the Mesopotamian plain. Life was pretty local, fairly egalitarian, it seems. They managed with, local irrigation for their crops, plus fishing, herding.
So what stopped them from scaling up earlier? Why didn't they build Eridu or right away? What was different?
Well, the really interesting finding here relates to a specific environmental feature, tidal irrigation.
Tidal irrigation, how does that work?
Okay, so during this period after the last ice age, sea levels were relatively high, what geologists call the maximum sea level high stand. The Persian Gulf reached further inland. And the key thing is the freshwater tides. The daily push of river water backed up by the incoming sea tide extended way up the Tigris and Euphrates rivers, much further inland than they do today.
Ah, so the rivers were effectively delivering water deep inland twice a day without anyone needing to build huge canals.
Exactly. The tides did the work. It was a predictable, reliable source of fresh water, potentially reaching places as far north as Nippur. It was essentially a free, natural infrastructure.
A shared resource that didn't require central management.
Precisely. It supported these decentralized communities. The environment was providing this critical service passively.
Which, counterintuitively, might have actually prevented early state formation because nobody needed to seize control of the water supply.
That's the core idea. But environments don't stay static, especially river deltas.
Right, they build outwards, sediment.
Exactly. The Euphrates carries a huge sediment load. Over time, its delta built outwards, it prograded. Eventually, the Euphrates River lobe merged with the delta coming from the Khuzestan area, forming the modern Shatt al-Arab waterway.
And this geological shift, it changed the water dynamics.
Critically, as the delta built out into the Gulf, the reach of those freshwater tides got shorter and shorter. That zone of easy, free tidal irrigation slowly retreated downstream, away from the inland settlements.
Okay, I see it now. For those established inland towns like Eridu or Uruk, the free water delivery system starts to fail. Slowly, maybe, but surely.
Correct. That passive environmental subsidy disappears. Suddenly, local passive irrigation isn't enough anymore. They face a water crisis.
And the solution?
The solution was large-scale fluvial irrigation, meaning actively taking water out of the river itself, digging massive canals, building weirs, diversion dams, huge engineering projects.
Projects way too big for one village or even a few villages working together loosely.
Absolutely. This kind of water management demands intensive, coordinated labor. It needs planning, oversight, maintenance schedules, rules for water allocation, especially in dry times.
And someone has to be in charge.
Someone has to be in charge. You need managers. You need rule enforcers. This, the research suggests, is what created the conditions for, well, appropriation, stratification, and inequality, as the source puts it.
The necessity of managing the new engineered water system forces the creation of hierarchy administration.
And ultimately, the centralized structures we recognize as the first states. Control the water, control the society.
Wow, so the changing shape of the coastline literally dictated the invention of government bureaucracy. That's quite a connection.
It really puts environmental change at the heart of social evolution.
And that lesson, that environmental shifts force fundamental changes, brings us, unfortunately, right to our doorstep. But now it's not a slow shift over centuries. It's multiple rapid changes hitting our oceans all at once.
Yeah, the contemporary research is stark. What really stands out is the concurrency. It's not just one thing. The oceans are facing, simultaneously, warming temperatures, increasing acidification from absorbing CO2, and declining oxygen levels, hypoxia, all happening together.
Okay, let's break those down. Warming seems the most obvious. What are the big impacts we're seeing right now?
Well, the confidence here is very high. Warming is causing huge shifts in where species live and how many there are. It's rearranging marine life on a massive scale.
Any examples of the speed?
Get this. Phytoplankton in the North Atlantic. Since the 1950s, their populations have shifted poleward by hundreds of kilometers, not over centuries per decade.
Hundreds of kilometers a decade. That's incredibly fast.
Staggering. Or look at Atlantic cod off Europe. Just a 1 degree Celsius regional warming between the late 70s and early 2000s was linked to a major shift in their distribution. And it's not just location warming, also seems to be reducing the average maximum size fish can grow to.
Which impacts fisheries, food webs, everything.
Everything. Now, layer on top of that ocean acidification, or OA.
Yeah.
Basically, the ocean soaking up our excess CO2, which lowers the pH, makes it more acidic.
How does that change things on the ecosystem level?
Well, chemically, it kind of flips the competitive landscape. Some things, like certain seaweeds or seagrasses that don't build shells, actually seem to do okay, maybe even better. It gives them an edge.
Okay, so some winners, but who are the losers?
The losers are the calcifiers, organisms that build calcium carbonate shells or skeletons. Think corals, mollusks like mussels and clams, echinoderms like sea urchins.
Why are they vulnerable?
The changing chemistry makes it harder for them to extract the carbonate ions they need from the water to build and maintain those structures. It takes more energy. And this stress is worse when combined with warming water.
Do we see this happening outside the lab, in the real ocean?
We do. There are natural analogs like underwater volcanic vents that release CO2. Around these vents, you see ecosystems transforming.
Yeah.
Shelled species like mussels disappear, replaced by fleshy algae, maybe some barnacles. It's a glimpse into a potential future.
And the economic cost. Corals alone must be huge.
Massive. Just looking at tropical reef loss due to warming and acidification, one estimate put the potential damages around US $870 billion by 2100 under a high emissions pathway. That's just lost tourism, coastal protection, fisheries, services we rely on.
870 billion. That number really lands the scale of the loss, but you said the real kicker is the combination of these things: warming, acidification, and low oxygen.
Absolutely. It's the synergy. They multiply each other's effects. Imagine an organism already struggling because the water is warmer than its ideal range.
Okay, stressed already.
Now add low oxygen, hypoxia, or higher acidity. That existing stress gets amplified. The organism's tolerance window, its thermal niche, shrinks dramatically. It becomes much more vulnerable to any fluctuation.
And these low oxygen zones, the hypoxic areas, they're spreading too.
Yes, oxygen minimum zones, OMZs, are expanding, both horizontally and vertically in the water column. This physically squeezes the habitat available for species that need a lot of oxygen.
Like active fish.
Exactly. Things like tuna, billfish, even smaller mesopelagic fish that migrate up and down, they have high oxygen demands. Expanding OMZs literally push them out of large parts of the ocean.
So bringing this all together, the Arctic often comes up as a place where change is happening fastest. How does that fit in?
The Arctic is like the canary in the coal mine, but it's also an engine driving global changes. We know the water flowing into the Arctic from both the Pacific and the Atlantic has warmed significantly just in the last decade or so.
And the disappearing sea ice.
The prospect of a seasonally ice-free Arctic isn't some far-off future anymore. And the loss of that reflective ice cover, well, it could mess with weather patterns, rainfall, far beyond the Arctic, and potentially much sooner than models used to predict.
Plus, there's the whole issue of thawing permafrost, isn't there, under the sea as well?
Yes, and this is deeply concerning. There's growing evidence, particularly from the East Siberian Arctic shelf, that methane has started to be released from the seabed.
Methane hydrates, frozen gas.
Exactly. As the water warms and the subsea permafrost thaws, these vast deposits of methane hydrates could destabilize, releasing potent greenhouse gas. It's a potentially dangerous feedback loop.
And on top of all that, the direct sea level rise from melting land ice, Greenland, and Antarctica, plus the simple fact that warmer water expands.
That's accelerating too. The rate of sea level rise measured over the last, say, 15 years is roughly double the average rate over the previous decades of the 20th century. It's not linear.
So it's not one crisis. It's warming, acidification, deoxygenation, plus Arctic feedbacks and accelerating sea level rise, all hitting concurrently.
It is. It forces you to realize we're facing the consequences of multiple rapid environmental losses simultaneously.
So let's try and recap this arc. We went from ancient hominins adapting with incredible ingenuity, turning elephant bones into precision tools out of necessity,
To the birth of states in Sumer, driven not by invention but by the loss of a natural asset, the free tidal irrigation, forcing a new centralized social structure over centuries.
and landing here now, facing this triple threat: warming, acidification, hypoxia, dismantling marine ecosystems at a speed that's frankly alarming.
The common thread is that relationship between human society and the essential resources, the environmental services provided by the planet. And today, Earth observation systems, satellites, sensors, they're giving us incredibly detailed data on these impacts. We can track the changes in acidity, temperature, habitat loss almost in real time.
Which is vital for understanding and hopefully for finding solutions.
Absolutely, for testing mitigation strategies for adaptation planning.
Okay, so let's leave you, our listener, with a final thought to chew on. We saw how in Sumer, the slow geological loss of one key environmental service, that passive tidal irrigation forced a fundamental reorganization of society over many centuries, leading to centralized power and stratification.
A slow burn forcing massive change.
Given the very high confidence we have in the current rapid accelerating changes, acidification, warming, oxygen loss changes happening over decades, not centuries, what kind of unexpected, perhaps equally fundamental shifts in governance, in economics, in global social structures might be forced upon us when critical marine ecosystem services, things like food security from fisheries, climate regulation, coastal protection from reefs and mangroves, when those diminish drastically, not over centuries, but potentially within our lifetimes or the next generations?
That same force of necessity that drove Paleolithic toolmaking and Bronze Age state building, it seems it's about to confront us again. But this time the clock is ticking much, much faster, a speed that human societies have never really had to adapt to before.
A sobering thought to end on. Thank you for joining us for this deep dive.
We'll see you next time.